Hello everyone. So this is my first YouTube video, and as the title of the video implies, I will be showing you how to effectively draw all the 20 amino acids. Okay. Something I really used to struggle with is really trying to understand why I need to know all the structures of the amino acids, or rather why they're important. And I will make a separate video on that. For now, we can discuss what are amino acids. Then later on, as we progress, we will answer the question of why do we need to know all the structures and why do we need to know each and every single one of them. Okay. So something you've probably heard a lot is that amino acids, okay, are the building blocks of protein. So what does that mean? I'd like you to think of this house here, okay? So when you see this house here, okay, this house had to be made from scratch. It had to have a process in which it was made. And the thing is, this house, okay, we use blocks, okay, to build this house. These blocks, we put them together using cement. We plastered the house, we painted it, we put window panes and everything like that to come up with this beautiful house. Okay, when you see a house, you are not going to start talking about, have you seen that structure that has windows and doors and bricks? No, you will say, have you seen that house, or have you seen that building, have you seen the mall? Because basically how the structure looks or comes out is what you call it. So you know what a house looks like, you know what basically a high-story building looks like, and amino acids are the same way. I'd like you to imagine this man, okay? This man here has his own blocks, which we call amino acids, okay? So the thing is, amino acids and blocks work in the exact same manner, all right? If we take blocks, arrange them together, we will come up with our house. We take amino acids, we arrange them together, we will come up with our human being. The thing is, amino acids are very cardinal because they make up the proteins, as we have just said. You can think of any protein whatsoever. You can think of a cow, you can think of a chicken, all right? You can even think about ifishimu. Okay. All these are proteins, okay, which will all stem from amino acids. So the thing is with the amino acids, you will get a cow according to how you arrange the amino acids, and as well as the chromosomes. You'll get a chicken and you'll get ifshimu according to how you arrange the chromosomes, how you arrange basically the DNA structure, and then you'll come up with these different animals. But we will get to that in a totally separate topic. Okay, the topic of biochemistry explains to you how you can build from amino acids to a full-grown human being. And it's not just one topic that's going to explain this. There are a number of topics that will come into play that will help you understand how these amino acids form a human being. And this forms your basis of medicine. If you want to be that medical doctor who saves lives, basically your biochemistry is the one, because any alterations in amino acids does lead to disease manifestation. So each and every time before I make a video, I will be telling you people the relevance of certain things and why I want you to know certain things, or rather why I think that they are very, very important. So let's get into it. We can start with the general structure of an amino acid. Let's have a look here, the general structure of an amino acid. So what is the general structure of an amino acid? So I'd like you to think of a family, okay? Let's say we have a family, okay? Here are the parents, okay? And then here we have the children, all right? See, the thing is, let's assume their last name is, this is Mr., Banda, okay? And then this is Mrs. Banda, all right? So these guys are basically the Banda family. So now, let's say you're in a banquet hall and you say, may the Bandas please come forward. All of them are going to respond. But let's assume here that Mr. Banda, his first name, let us call him Tyson Banda. Okay. Let us call the woman Neo Banda. Let us call the girl here, all right, Helen Banda. And let us call the male here, Romel Banda, okay? So, here, all of them have got the last name Banda. So if you were in a banquet hall and you say, may the Bandas please rise, all of them will respond. But if you specifically say, may Mr. Tyson Banda come forward, then only Tyson will respond. If you say, may Miss Neo Banda come forward, then only Neo will respond. If you say, can Helen Banda come forward, then Helen will respond. If you say, Romel Banda come forward, only Romel will respond. The reason for knowing this information is because amino acids basically have the same last name. Amino acids have the same last name, okay? So basically, what is this last name that I've just basically talked about here? What is God's name in this last name? This last name is the general structure of an amino acid. Basically, all the amino acids are going to have this general structure. But the kicker is their first name is going to be different. This is what differentiates the amino acids. So basically what you're trying to say is, okay, these amino acids, right? They all have the same general structure, which is their last name. But their first name is different, which differentiates the amino acids all together. So basically that's all I'm trying to say. So let's get into what the general structure of an amino acid actually is. Like, what does it actually look like? Now let's have a look, see, at the general structure of an amino acid, that basically which we call the basically the last name. So basically we can begin with let's talk about the first name for a start, okay? So let's say we have this person called Neo Banda, right? We've established that the last name is basically the general structure of an amino acid. The first name is what we call a functional group. So when we write the general structure of an amino acid, we symbolize a functional group with an R, okay? So this R is now going to be bonded to the general structure of an amino acid. So this is our first name, Neo, which is our functional group, which is R. So we call R is equal to the functional group. Something that's very important for amino acids is understanding bonding. I'm not really going to get into deep detail in the organic chemistry of bonds, but I will make a separate video on that. But I will give you a couple of heads ups in certain information you should know. So now, I will draw the general structure of an amino acid in red. I prefer writing my bonds in pencil because it does give me an opportunity to erase if I make mistakes, okay? So basically, our functional group is attached to a carbon atom. See, the thing is that a carbon atom can only hold a maximum number of 4 bonds, okay? So meaning when you are drawing your amino acid, at the end of the day, when you are counting the bonds, they should only be 4. If it is more than 4, your answer is 150% wrong, all right? So now this carbon atom is going to have 4 bonds. 1, 2, 3, 4. So what is each of these bonds? What is each of these bonds attached to? See, this carbon atom is going to be attached to what we call a carboxylic group, which is a carbon atom, okay, attached to 2 oxygen atoms, all right? But here is where basically the catch is. See, one of the oxygens is gonna have a double bond, okay? But then another one of the oxygens is only gonna have a single bond. See, the thing is, doing this, what it basically does to this structure here, it makes it very unstable. I'd like you to think of this oxygen atom as a married woman. I don't want to say married man because, you know, men can have more than one wife in particular. So let's not look at married men or married women. I'd like you to think of this as a married woman. She's already married to this carbon atom over here, so she cannot accept any other. But I'd like you to think of this oxygen atom here basically as a woman dating a married man, okay? She is craving stability. The chances that a single woman will be faithful to a married man forever are very, very, very slim. Because if a man shows up at her door and offers her marriage and more stability than this man is offering, she will definitely leave. So because this woman, or rather this oxygen atom, is unstable, it can easily leave this carbon atom here. And we symbolize it by putting a negative charge. In all your reactions, this part is the most unstable, and it will always conform to change because it craves stability. Okay? So the thing is, this is shortened as COO minus. Or you don't even have to put a circle, or you can just write it like this. So remember, this negative charge symbolizes like O to the carbon atom, there's only one bond. This one has got no negative charge because it has got stability. So let's find out, what do these 2 bonds have, okay? See, the funny thing is, this carbon atom will be bonded to a hydrogen atom, all right? But then here we are going to have ammonia with a plus on top. Why do we have that? See, ammonia is very funny, you know. Ammonia, okay, can either have a positive charge or have no charge at all. Why is that? See, ammonia, okay, can hold a maximum of 3 bonds. I'm terribly sorry about that. 3 bonds, all right? See, when it has 3 bonds, it is basically full. It cannot accept anything more, so there is no charge. So what happens is this. The ammonia can still attract an extra hydrogen atom. Think of it like getting a side chick that will kind of like roam freely next to it, okay? Kind of like a very strong attraction, but still easily donated, okay? From your physiology, you learn about buffering systems and how your blood becomes acidic if basically your blood has got too much hydrogen, but I do not want to get into the physiology of that. That will be a topic for another day. So the thing is, why does this have a positive charge? Let's establish it, okay? This is one bond. All right, so we can put our nitrogen here, okay, to one bond, assuming it is attached to this carbon. So there are 3 hydrogens. 1, 2, 3. Okay? So basically what this has done is, I want you to imagine that this hydrogen is the one with the basically strong attraction. This is like a hydride ion. It's just not exactly bonded, but kind of like a strong attraction. This is your carbon here, this is a hydrogen, and then this is a hydrogen, okay? So now, the thing is, we have 4 bonds. This is what is causing the positive charge. Here we have 3 bonds, so there is no charge. So 3 hydrogen ions, which is 3 hydrogen ions, plus the 1 bond to the carbon atom is going to be equal to 4. And this is why for the general structure of an amino acid, you've got this positive charge. So how do we write basically the general structure of an amino acid, okay? We have established our R, which is our functional group. I prefer to write it in this method, but if you guys prefer to symbolize the bonds, it is still fine, but for me, I prefer it in this manner, okay? And then you show your bonds, okay? So this, ladies and gentlemen, is your general structure of an amino acid, okay? So now we can actually now look into how to draw each and every single one of these amino acids, associating it to the general structure. Now that we know the general structure, the only thing we will constantly be doing is changing the functional group. So just for clarification, we can count the bonds. This carbon atom is bonded to this one with 2 bonds. So 2, 3 plus this one, 4. 1, 2, 3, 4. This carbon atom is bonded to 4 bonds. 1, 2, 3, 4, which is the hydrogen atom. 1, 2, 3, 4. And then this functional group as well, we will always pay attention to the bonding. Finally, this nitrogen atom here has got 3 hydrogens plus the hydride ion that is kind of like creating a strong attraction, giving it a positive charge. See, this is what we call the Zwitter ion form because there's no net charge, because this one and this one, positive, okay, and the negative cancel each other out, giving this no charge, but that is a video for another day. So we will begin our amino acids by looking at alanine. So let's have a look at the amino acid alanine. The reason why I like to start with alanine or alanine is because alanine is like the only amino acid that you need to know. And once you know this one, you know the rest. So what is alanine? Alanine is basically a methyl group attached to a general structure of an amino acid, okay? And I have written down these notes, but I am making a separate video for you guys. So if you're kind of worried, like, oh, I'm talking a bit too fast, slow down, I have written these notes, okay? So what is a methyl group in the first place? So in your organic chemistry, we have the hydrocarbon. So I'll start with methane, okay? So methane is basically a carbon atom, okay, bonded to 4 hydrogen atoms, okay? Earlier I mentioned that a carbon atom can only hold a maximum of 4 bonds, okay? And that's a very strict rule of organic chemistry. So basically what's going to happen is, see, this methane needs to attach to the general structure of an amino acid in order to make alanine, okay? But how does it do that? It needs to lose a hydrogen ion. So now the rule of organic chemistry is this. Whenever you lose a hydrogen from a carbon, you end it with the suffix YL. So basically, we are going to attach a methyl, okay, group to the general structure of an amino acid. So what is a methyl group? A methyl group, okay, is an incomplete methane in brackets. So what it is this: we've got a carbon atom here with a bond here, a bond there, a bond there, a bond there, okay? And then we are going to have 1, 2, 3 hydrogens. But here, we're not going to have a hydrogen ion. We are going to attach it to the general structure of an amino acid, and I will just put it as a star to symbolize that it is attached to the general structure of an amino acid, okay? So that is why it is called a methyl group. Methane is CH4. Methyl is CH3, okay? So what I'm going to do here is, we've established that our methyl group has got 3 hydrogens, okay? So this is how we're going to draw alanine, all right? So we are going to have basically a carbon atom bonded to 3 hydrogens, okay? And then we will attach it to the general structure of an amino acid. Remember, an amino acid is CH to COO minus 2 NH3 plus. And then always show your bonds, okay? So you can shorten this by simply writing H3C to CH to COO minus 2 and H3 plus. Okay, so always make sure you count your bonds. So we can count together 3 hydrogens plus 1 bond here means 4. 1, 2, 3, 4. This one has got 4, so there's a positive charge 1. This one there's 2 bonds, 1, 2, 3 plus this one 4. And this is your general structure of an amino acid. And this is our functional group, which is a methyl group. So now we can look at the next amino acid, which is phenylalanine. Now we can look at the amino acid phenylalanine. So what is the structure of phenylalanine? Funny thing is, this is how I like to look at it, okay? The name is phenyl, okay? Alanine. So phenylalanine, okay, is a phenyl, all right, attached to the methyl group of alanine. So in short, we will take alanine and attach a phenyl group. So we established that alanine is this, a methyl group attached to the general structure of an amino acid, okay? So I've made strong emphasis on the rule that a carbon atom can only hold a maximum of 4 bonds. So this one basically, the bonds are full, meaning we need to lose a hydrogen in order to attach this phenyl. So what is a phenyl group? A phenyl group is just a 6-membered ring. Okay? So what is this 6-membered ring? From your primary school, this is a hexagon. But because we are adults, we cannot say a phenyl ring is a hexagon with double bonds inside. We need to confuse our children. So when your babies are asking you, oh, I need help in my shapes, you should be helping them because it also means they're studying. So basically what we're going to do is this. We have a hexagon from your primary school. And just to put you at ease, we can count them together. This is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Okay? So now, what we're going to do is we're going to add double bonds within this structure. We'll put a double bond here, skip this one, put a double bond there, skip that one, and put a double bond there. And this is your phenyl or benzene ring. This is your phenyl, or you'll see it called a benzene ring. Okay, so the thing is, what we're going to do here, all right, we are going to take this benzene ring, okay, and attach it to the methyl group of alanine. So what's going to happen is this: we are going to lose this one to create space for this ring. So this carbon atom now has the freedom to create a bond there. So what's going to happen is this: we are going to have this. We have our ring there, ever so nicely, and then we establish, you put a bond there, skip that one, put a bond there, skip that one, and put a bond there. Okay, so then we have our carbon atom bonded to a hydrogen there and a hydrogen there. Okay, and then at the end of the day, all right, we attach it to our general structure of an amino acid. And we can shorten this again by symbolizing it like this. Okay? Preferably, whichever one you're more comfortable with, you can either shorten it or leave it expanded. It's entirely up to you. At the end of the day, always just make sure that your bonding is at par with the rules of organic chemistry. So your hydrogens now become 2, so it becomes CH2 instead of CH3 because we lost this hydrogen there, and then we attach it to the general structure of an amino acid, all right? Now we can look at the next amino acid, which is tyrosine. So the other name for tyrosine is hydroxyphenylalanine. So basically, tyrosine is just an addition of a hydroxyl group onto the phenyl ring of phenylalanine. I know, not difficult. So let's establish this, okay? We established that phenylalanine is a phenyl group attached to the methyl group of alanine. Tyrosine is just basically a hydroxyl group attached to the phenyl ring of phenylalanine. That's why its other name is hydroxyphenylalanine. You will understand the significance of this because tyrosine is a derivative of phenylalanine. And I will get into essential and non-essential amino acids. As of now, I just want you guys to know the structures, and then I will go into each and every single detail of each and every single one of them, how they make enzymes and whatnot, okay? So let's remind ourselves again the structure of phenylalanine. Now let's kind of like remind ourselves. Okay, as usual, always remember your bonds, okay? So basically, remember this one becomes CH2. That's the general structure of an amino acid. So now let's compare it with tyrosine, okay? So basically, it's very, very easy to do. See, the hydroxyl group is just basically OH. Remember from your dissociation, if you don't remember, when you break down water, you can kind of like have this, the hydrogen ion, right? Plus OH. 1, 2, 1, 2. So basically this is it. If you don't remember this, please go back to your organic chemistry. But if you'd like a video on some of these basic concepts, you can just hit me up in the comments below and I will make something for you guys. Alright? So basically our hydroxyl group all right, is just basically OH. The only thing we're going to do is attach our hydroxyl group over here. That's all we're going to do. Remember that these bonds, this is a carbon atom here, carbon atom there, carbon atom here, carbon atom there, carbon atom here, carbon atom there, okay? All these are carbon atoms, and we established that this is a hexagon, a 6-membered ring, and then we include double bonds inside. So basically, you're just going to attach this to the parallel end over here, and just like that, you have made tyrosine. So let's do that, okay? Ladies and gentlemen, this is how we have made tyrosine or hydroxyphenylalanine. Now we can have a look at the next amino acid, which we'll have a look at is aspartate or aspartic acid. So we're going to have a look at aspartate first, and then afterwards we're going to have a look at glutamate. I kind of like to compare these two side by side because they are basically the same thing. And it's not, they're relatively like impossible to confuse. So what is aspartate? Aspartate is just the addition of a carboxyl group onto the methyl group of alanine. Remember that a carboxyl group is COO minus, okay? So remember that alanine we established it as C to CH, COO minus. Remember the bonding rule, right? Our rule of bonding is that a carbon atom can only hold a maximum of 4 bonds. So we have to attach this carboxyl group here, okay? So remember, okay? So basically I'm going to write it like this. Still the same thing, but the reason I've done it like this is because what I'm trying to symbolize is that what is bonding to the next atom is the carbon atom. Okay, so preferably you have to symbolize that the carbon atoms are the ones doing the bonding. So this from CH3 will become CH2. Okay, why does it become CH2? As we established previously, it needs space. So this one is just this one. So you really don't have to struggle by trying to remember each and every single one amino acid. Just draw alanine and then manipulate it continuously, all right? So then now we copy the general structure of an amino acid, all right? So remember, aspartate or aspartic acid is just a carboxyl group attached to the methyl group of alanine. So what is glutamate or glutamic acid? Glutamate is just the additional methyl group of CH2. See, I don't know if CH2 is still called methyl. I think it's called the methylene group. Should be methylene, but let me know in the comment section what this one is called, CH2. So you are just adding this additional CH2 onto the CH2 of aspartate. That is all you're doing. You're just copying this. So in short, this one, instead of there being 1, for glutamate, they're going to be 2. Okay, that's all you're going to do. And that's why I kind of like to draw them side by side. So CH2, that's your first one. This is your second one. Okay, and then you attach it to the general structure of an amino acid. Okay, there we go. So basically these two belong to the same family, but we'll talk about families another time. So all you have to remember is aspartate is an additional of a carboxyl group onto the methyl group of alanine. Glutamate is an additional methyl or methylene group onto the methyl group that aspartate attached to on alanine. This one in particular, attach another one, okay? After you attach another one, attach your carboxyl group. So instead of having CH2, you are going to have 2 of them instead of 1. And that's all. Now you're going to have a look at another set of amino acids I like to put side by side, which is asparagine and glutamine. The thing is, asparagine and glutamine, funny thing, what I always say is, like, when you think of INE, think of NH3. So asparagine and glutamine have got no charges, okay? And I will establish why I've said that. So why have I said when you see INE, think of NH3? See, this name is vaguely similar to aspartate. And this name is vaguely similar to glutamate. See, the thing is, we've established what these glutamate and aspartate look like, but I will draw it again to remind you guys. So remember, we established this one is CH2, okay? And then attach it to the general structure of an amino acid. And then remember, we established that this one, instead of being 1 CH2, we are going to be 2 of them. So now, we have aspartate, we have glutamate. But this one, we just put INE. So instead of glutamate, it's glutamine. Instead of aspartate, it's asparagine. So, what in God's name do they look like? I mentioned something earlier that these oxygen atoms crave stability, so they can easily be donated. So, basically, we are just gonna donate these oxygen atoms, okay, to leave space for what we call an amide group, which is NH2. So aspartate is the addition of an amide group onto the unstable carboxyl group of aspartate. What does that mean? We've got 2 carboxyl groups. This carbon atom is known as an alpha carbon, meaning it is attached to 4 different groups, okay? So the one that is we're going to target is not the alpha carbon, okay? Basically, the one that the amide group is going to attach to is this one here, not the alpha carbon. This one is called the gamma, but anyway, we'll get into alpha and gamma another time. So basically, you are not attaching your amide group onto the carboxyl group that is attached to that is on the general structure of an amino acid. You are attaching your amide group onto the functional group. So how are we going to do that? I will show you how. Remember, so I'm going to expand this for you just to remind you guys. Remember, we established that this one is has a double bond there, okay? CH2 to C. H to COO minus. Okay, so this is how we are going to draw our asparagine. Okay, how are we going to draw this? We're going to attach an amide group, and an amide group is merely just NH2. That's all it is. And we're done. And we do the exact same thing for glutamine. So, glutamine, okay, is just gonna be this, and then we attach an amide group. So it is basically N, okay, with an H there, to this, and then an oxygen. 2 of them, And then this is your general structure of an amino acid. And we have established asparagine and glutamine. Now we can look at another set of amino acid called, basically I like to group them together with basic amino acids. So the next group of amino acids that we're going to look at are the basic amino acids. So for the basic amino acids, the first thing I like to do is write down the mnemonic leggings are basic. So what this means is that we are basically saying this histidine, we have lysine, and we have arginine, okay? So the thing is, overall, basically we are going to have a net positive charge to produce the basic amino acids. And I'm going to show you how. On our general structure for the amino acid, we say there's no overall charge, meaning there's no net charge. So we can start with the simplest of the basic amino acids, which is lysine. So for lysine, we are just going to have CH2, 4 of them. And then we attach it to the general structure of an amino acid. 1, 2, 3, 4. Afterwards, all you have to do is attach it to the general structure of an amino acid. So once you do this, there is no overall net charge because these two cancel out. In order to produce the positive charge for the basic amino acids, what we are going to do is add NH3+. Why? Because this charge is basically what gives us our basic group. Well, basically, we want this positive charge because it symbolizes that it belongs to the basic amino acids. Since we've had a look at lysine, we can now look at histidine.